Can you listen to me? Please say yes if you can listen to me. Say yes to the chat if you are listening to me. Thank you. We'll start shortly. Let's the number of viewers becomes more than 10, so we'll start. I believe we have almost like 18 person registered in the workshop, but about 12 or 15 numbers if they are viewing right now is fine. So I sent you some data today. You need to download those data and get them. I hope that everyone got the software according to your responses. There are just a few, probably one or two, who still haven't installed the software. But that's fine. They can follow along. Anyway, I cannot keep you waiting. I will start right away. So what I have sent to you, I have sent you some data. So data is supposed to go where? Let me go to the data supposed to go home if you have already installed the software. Uh, I sent you velocity. That's one of the files I sent you. So this file is supposed to come here under velocities. And I sent you also two other files. They are named scale. They have the extension scale. These two are supposed to go where? In this directory, scale directory. One of them is tar, the other one is soil. I'm numbering them according to the job they belong to. So this file will use it for the job name tar. The only difference in naming is the extension. The job files, they have the extension jobs. In here, I'm having an extension CL, scale. So I gave you, I believe, these two files, as well as another file which is supposed to go in velocities. And by the way, you can open them. There is no how, but don't modify them. You can open them with what you can open them with Notepad if you have Notepad or any other text editors. One of the good text editors which I like is Notepad++. That's the one. This is one of the best for Windows. It does not have versions for Mac and Linux. But those are the files, or this is the content of the file. I created them using the software. Why I'm giving them to you? I'm not letting you to create them yourself, because the idea is that you run the jobs, you learn something, and these things, they're not tedious or time consuming, but we cannot, I cannot keep you waiting while I'm explaining. So it's better you have them. And during today's session, I let you know how I create them. So launching the application, I'm having the application here, my desktop. The first window I'm supposed to get is the launcher. That's the launcher. So the last time I believe we stopped in job 01, which is uh, muting. We mute the fractions. I will go review right now the same job and let me check how the difference I made to the one you have. What's the most difference between mine and yours? So right now, as I have said before, the total number of jobs might go up to 40, probably, or less than 40. I'm still not sure. But according to my plan, we go might up to 40. For today, we might just finish tar and swell, job 02 and job 03. The rest are ready, but let you do it yourself. I'm seeing some students are still not installed the software. Let them get that software. Let them do also the first quiz. So after the first quiz, we go faster. We probably do like 8 to 10 jobs per day. But for today, we'll go cover. I will redo again this one. This is we have done it together. I did it last time during my streaming. But the news, I do it again today, and I show you some differences. And those differences, we apply them to the next two jobs, and they might be applied again and again and again in the rest of the jobs. So if I go back to news, I open it, that's how it's supposed to go. I read my data. If you have followed my outline, I have done something. I have made a small copy of the data instead of getting all the data, because here we are right now. Up to this point, I'm in testing stage. I haven't written any new data. I haven't copied the data and applied some processing and saved the data. So this stage is still a testing stage or Q stage, or even they name it parameter testing. So I check what are the best parameters for each step. For example, for today we'll be doing spherical divergence correction. I let you know what's spherical divergence, and we try to remove some noises. A noise which is very common in marine data is called swell noise. I let you know what is swell noise. So if I go back to my job here, new jobs. So I'm first of all I'm reading the data. I'm not reading the big file. I'm reading only the selected file. So in this I can select, for example, 500, because shot 500, the shot, that's the primary key, is part of this data. So this data contains 8 shots. The first one is 200, the next one is 300, up to 900, and the interval is 100. So the second key, I'm getting the data as shot, in shot number, and I'm sorting them according to their channel. So the first channel is closer. The first channel in this case is the farthest channel. Is the channel farthest away from the source location. The last channel, which is 120, is the nearest channel to the shot location. So this is supposed to be have done by you. I make a small difference. There is a parameter in here. If you go down, number of repeats, n repeats. What does this do? This will read the data more than once. So in this case, I'm reading them only once. So how about if I read them twice? So let's try to run it. I'm reading the data twice. What you see? So I'm getting two data. I read them twice. I'm supposed to give one shot, which is 500, but I got two shots instead. And I'm getting some panels. The first one is empty. The next one having two gathers, and the mute is applied. So let me bring something. Let me bring some job controls. So here again, I got to add in job controls. I bring something called if. It's kind of like programming. It's not complex programming in here. We say we bring it before the mute, and we bring what parameter we want to apply the mute on. In this case, I want it to be applied on one of the repeats. So repeat is not a real trace header, but uh, it's part of the trace header in this software. It's not a real trace header. Those are the values you see in here. They are list of all available trace headers. So CDP channel number. Have you seen the channel number? The one we were saying is 1 to 120. That's the channel number. Have you seen the coordinate scale? We use here the coordinate scale. What exactly is coordinate scale? Coordinate scale is a number you multiply to the location. So let's assume that my location is 10. The choosing location is 10 in the X domain and 20 in Y domain. So if I choose a coordinate scale like not 1, I'm specifying it as 1 in my in this job or this module set header. I set it to 1, equal to 1. But you can change it to whatever value you want. It can be 10. So the coordinate will be multiplied by 10, whatever the coordinate you have. If in case it's 10 and you are having coordinate scale 10, the in value, the in number gonna be 10. So in this case, we go to the are sorted alphabetically. We go select repeat. So I select the repeat. In which of these repeats or which of these data I read them twice? The first one I want it to be applied, the mute to be applied on the first one. The second one as kept. I keep it the original one. But you know most of the software programming, whenever there is if, there's supposed to be an int. Some programs they don't require int, but in here this program is written by basically written on Fortran. Fortran is one of the programming language. So I go to job controls again and I bring indif. Where is indif? Let's see, that's indif. I bring it here. There is nothing you can modify. Whenever you get this many no fields to change, it does not accept any parameters. So if accept some parameters, I'm just stating I want to use the repeat as my control, and I apply it to first value. Where is from where I'm getting the repeat? The repeat is here. So if I run it right now, let's see the difference. Oops. Maybe I'm doing something wrong. Let me check. Number of samples. That's the mistake I have done. So it's one sample. It's not. I'm reading only one data. Previously there were 8, but right now I'm reading only one. So that's the change I'm supposed to make. And it's mandatory change. Whatever the color in red in any module, that's a mandatory field. So if I run it again, so this is which one I applied the repeat on. I believe I applied it on 1. So that's what you see the difference. That's a good thing. Whenever you apply anything, it's good to see the difference. What exactly is changed? So let me change the scale, make it smaller. The scale is my PC is different than here. Let's vertical scale. I make it 2 probably. I run it again. So I'm seeing all the data right now. So let's see the difference. That's good thing. So at least we are removing the refractions and we are muting anything above this line. So whatever the value was of each trace, traces are made of samples. So first sample, second sample, third sample, and so on. So they were zeroed. They were given a value of zeros. So the trace mute module was doing simply zeroing out all the trace samples above the line you specified. That was the line you created. Another thing which is very useful is to plot a difference. So this minus this, sample by sample, they're supposed to be having the same probably geometry and everything's supposed to be the same in terms of not filtering but geometries. So if I go activities and plot difference, 2, 1 panel, and what I'm outputting 2 minus 1. So if I run it, so that's the difference. So I hope this is useful. Another thing which is good always to view is the log file. Whenever you run a job, you will get a log file. Why I'm having 240? What is exactly 240? 240 is the number of traces you read. So what is the traces I read? Because I'm reading one gather only. If I go back to my job, you have seen that I'm reading one gather, which is 500. Gather number was 500, but I'm doubling. I'm reading it twice. So 120 times 2 is 240. So it also states what each one does. So let's see this mute function. Because I'm only reading one of the repeats, it's not applied on both of the gathers. It's applied on one of the gathers, and that's the reason I'm having a value of 120. So let's move and do another job. The job I made it already, so it's already made instead of me going creating the job during the streaming. Might be time consuming. The parameters and the sequence of the job is already sent to you, and all the parameters they are available within the handout I sent. But a good point is how I can use include. So if I have a job which is made and ready, and I'm creating right now a new job, how to bring parameters from previous jobs? Why should I create like modules from the beginning if I have a job which is almost similar? You can use the include. So if I go say I'm creating a new job and I want to bring some modules which are ready in a job number 2. So I can select them. I can select 1, 2, or whatever value. If you want to select multiple, you click and move down. Double click and move down. And just click OK. Or you can select all of them. Basically, the first one will not be selected because it's already live. So let's, for the time being, skip this one, save and exit. Let's create, because I already have created it, I show what are exactly the parameters. So let's use job 2. The job is supposed to be in a folder or directory named jobs. So this is the second job, TAAR. So what TAAR is? Two amplitude recovery. What does two amplitude recovery is? I go back to my slides. So two amplitude recovery, and we use test. We manipulate header using trace. This is one of the modules we're going to be using. We use a scale. We scale our data as well, and we go up to where we finish up to here. So next time we will use FK filtering, spiking deconvolution, spike detection, not spiking deconvolution. Spiking deconvolution, we'll do it in another session. So these are, and some more even. This is quite heavy. We'll do it for the next session. So refresh and mute. This part I believe is completed. Yeah, we have reached up to this point. So what is amplitude recovery? Whenever I talk, the person very close to me, he's supposed to be listening to me and hearing my voice very clearly. And the person who is very far away from me, he might not be or having difficulty listening to me. Why is that? The simple idea is my voice or the energy of my voice is lost while traveling. The same thing happens to seismic energy. Once the blast or the air gun is fired, it goes to a certain limit and the energy gonna be lost. That thing is called spherical divergence. You created an amount of energy, and this energy, as it's propagating, it's occupying more and more volume. So you energy, the amount of energy at later time, at later stage, is smaller. The percentage for each volume is small. So while stay at shallow or near times, area times, I have a lot of velocity, a lot of energy in small volume. So this phenomenon or this idea in geophysics called spherical divergence. Spherical divergence is different than attenuation. Attenuation happens due to friction, due to friction, or due to loose material. Subsurface material might be like a material which cannot transfer the energy, so the energy is lost. We are not talking about that type of energy loss, and that type of energy loss cannot be compensated or corrected easily using what we are doing today. We use different models. That's not called true amplitude recovery or spherical divergent correction. For those things, we need to use different type of corrections. In fact, we are not going very deep into in this workshop. So here I'm having an amplitude trace, a simple trace, and that's the amplitude of the trace. So this is the amplitude of the trace, and I'm going deeper. So what happens? What you see is that the energy, the amplitude decreases, and because the energy is lost. What my purpose is boost those later times without changing the shallow times or early times. That's what is called amplitude correction. And how it's done, the basic idea, the basic function is one velocity squared multiplied by time, two-way time or travel time. So why two-way time? Why not one-way time? Because in seismic, except direct travels from source to G4, so that's one way. But the rest, the travel time is usually two-way. It goes down, hit our formation or a reflector, and gets back to the sensor. So it travels twice. It travels to the point, to some subsurface point, and reflected back. So that's the basic equation, but it might be more complicated than this. So everyone is using different type of equations, but the idea is basically the same. So So here are the details. You can follow this yourself, and I'm explaining in here how you can apply these things and what each parameter is doing in each job. So this is the job name. That's the job name. And these are the sequences of modules we are bringing. And I'm showing also you what are the different parameters you have to set. So for example, the first module, number 2, is the script. We again read the disk. So in this case, once you want to create new job, it's better to use include. Use include because you already have this sequence. You have done the script. You have this new. This is something new. You have set header in a previous in job 01. So just go use include and bring them. You can select multiple modules. The rest looks different. So I will explain what exactly we are doing with the rest for today. So if I go back to my software, I select the job. That's the job. So the first one is the script. What is the only difference in here? I read it 6 times. I'm not reading it once. Instead of one, I read it 6 times. And I read only, I have eight shots. I read only one of them, which is number 500. The number of flash shots is 500. And I'm sorting them, the secondary key is channel. So I click OK. This is already has been explained, so that's very similar to what we have done before. It's gonna be longer and longer, so by like job 8, you'll find it up to this point. So this is the testing phase. We are testing the parameter. When we reach a production stage, whenever you find that there is a disk write, so you are saving your data. You are happy with some parameters and you are saving your data. In that case, you are in production stage. Production, you are producing something. You are producing data, new data. You are creating new data. So production, oil industry is quite different than production in seismic data processing. So what we see, it's quite long. There are 14 modules. The first one comes by default. What is this one? Yes. So what is this one? This is very important. Whenever I do uh, amplitude recovery, I need to know the spacing between traces. What is the spacing between traces? And what is the space or the offset from the shot location to the first geofold? So if I go back to my slides, let me explain to you something in here. So this is a good example. This is a shot. I'm having traces from 1 up to 120. Where do you think is the shot location? Think about it. I'm not expecting an answer. If you can answer if you think you know which side is it, I say. So is it to the right side, left side, or the right side? The shot, is it somewhere here or on the other side? Let's see who can answer in YouTube. Oh, there is some lag. So the lag is probably like 1 minute. Anyway, I'm not sure if I can wait for 1 minute. Where do you think is the shot location? Is it to the right or to the left? That's correct, Hamza. That's correct. That's to the right. And why? That's very simple. Let me go to my slides. Because the energy arriving in here, it's arriving at area times. It means the shot was fired in here, and the energy point are reflected to this trace. So it took least time to arrive back to the geophone or the hydrophone in this case. But this one, which is farther away, it took more time. So let's assume that this is my shot location. It goes hit the ground, hit the seabed, and get reflected back to this hydrophone or this place. It's not single hydrophone. There might be a group of hydrophone. So they name them group, receiver groups. There might be like six hydrophones together. They are getting one. They are providing only one trace. There might be 12, 24. 24 is good number. And why is that? That's not our topic for today. But what exactly I'm doing in here? I'm saying what is channel? What is I'm bringing a name, and that name I'm bringing it from a trace header. So go, I'm saying asking the software go to seismic trace headers, and there is a trace headers called channel. Bring it. How do I know that there is a trace header named channel? Go to trace headers. That's the convention, and get a trace header named channel. Then I specify another parameter called delta, 120 minus channel. So channel 1, if the channel is 1, 120 minus 1 is 119, and so on. So it changed according to the channel number. But from where I got the channel number, if I go back to here, let's go to seismic and analyzer. Let me select, this is my selected shot. So its size is quite small compared to the old data. Old data, the size is more, I think it's 650 megabyte. This is only 6 megabyte. So if I select this one, if I go back to trace header, this is the trace header. So I'm saying go seismic trace headers. Go to seismic trace headers. And there is a trace header. The name of that trace header is channel. Where is that channel? Here is it. So this is the convention in SIG-Y headers. But why this one are blue and the rest are red? Sorry, black. Why this one is blue and the rest are black? In SIG-Y standard, up to 180, those are the one usually assigned already. Those are extra headers the user can input or can specify. So in this software, Claritas, they specify their own headers. So each trace has a short ID. Each trace, so these traces are still 200. So if I go to the next trace, still 200, but the channel number is 2. How is that? If I go back, so this is still I'm 200, but channel 1, 2, 3, and so forth. When it's supposed to change? When it's supposed to change? When I supposed to go like to the next one? In this case, in this data, the next shot is 300, is not 201. So when the channel number goes to 120, I'm not going to do it, but that's how you go to the channel and check the values. It does not tell you the data, but it gives you an idea of what are the trace headers and what are the values. Anyway, let's close this one. Quit and discard. Let's go our module. So I'm saying I'm specifying another parameter called delta. And the delta 120, that's the total channel numbers I'm having, minus the channel. So if I read the first one, 120, the first one is uh, is the is the farthest one, is the one to the end. So here is it, the last one. So if I read first one, that's the delta, the difference from the first one to the last one. First phone or first channel to the last one, that's the delta, and so forth. Then I specify an offset. That's what I need. I need the offset from the shot location to any of the traces. So that's this number here in meter is the spacing. I already told you about this. Where you find this one? I think you're supposed to find it here. That's the near offset. So this number is the near offset plus delta times 25. Why 25? Because the trace spacing is 25. Space is 1D space. They are 1D data, straight line. There are not a lot of lines. The hydrophones, I'm assuming they are on a straight line. So the spacing, I multiply plus, because that's the first one, plus the delta times 25. That's the test spacing. Let's assume I'm at first, let's get what is the spacing of first one, first resident. So channel, I get the channel number one. No, channel number two, first channel is 20, 120. The first one is 120. So I go back here. Wait for a second. Let me see a good gather. Oh, yeah, that's the one. So the first one closest to the shot is 120. If I go back to my math, so first channel is 120, the closest to the source. So 120 minus 120 is 0. So all this is going to be 0. So the first offset from the first closest to the source is 258. And once I'm done, what I'm specifying, I'm saying to the software, go back to trace headers, go back to the trace headers, specify the trace offset value as the offset I calculated. So specify the offset as the offset I calculated. So if I don't need to go open SIGA trace headers, but there is a trace header called offset. So each trace is supposed to have its own offset. Offset from the source location. The offset can be 1D offset or 2D if the data are 2D. In this case, they are 1D, so the calculation is very simple. So I'm done with this one. If I go back, set header, I talked about this coordinate scale. What is the value supposed to multiply the XY location? So I'm not multiplying by any other value other than 1. So that supposed not to be changed or divided. The division is minus. So if you minus some value, it means you are dividing the offset or the x location, or the y location. There is no y location in this case. That means that you are subdividing them by the value you provide them. So this is a simple module, set header. You can bring whatever header you find. How we can check the headers? What are the different headers? I already told you. You go to SIGY analyzer and you find what are the trace header names at least. Those names can change from one software to another. So in this software, they name them code underscore scale. In our software, they name them differently, but you can check what are the different headers. Another way to see the headers, uh, if you go to help or help, let me see, there is, do you see CD1? Yeah, there is. So these are different headers, usually in CD1. So one of them is offset, distance from source to receiver. Coordinate scale, scalar to be applied to spatial coordinates. The source x, y, receiver x, y, CDP, they will be multiplied by this value, whatever value you give. So if I go back to my job, close this one. I'm done in here. Then I go use if, a job control. Job control set headers, you might ask, how I know from where to get them? Set headers, if you go to add, is supposed to be in trace headers. If supposed to be in input output. It's not easy to know them, but if it's hard for you to know them, I recommend going to alphabetical listing. So they are listed according to their names. So that's easier. If you don't know from where you can get them. But for example, X view is supposed to be in plotting, balance, interest, balancing, trace scaling, and not, and so on. Panel text is also in panel text. Talk about panel text is in plotting too. If they are all in job control, I control the job. S mute is in mute, I think, trace editing. Myself sometimes trace editing, okay. Yes. So there are a lot of modules. Cancel. Then if I go to in here, in if, what am I doing? I'm taking the repeat from the list. So I'm reading the data. How many times? I say it 6 times. So I apply spherical divergent correction. Spherical divergent operator I applied on the data I read, but not all of them. First one, I does not touch it. The first data I read does not touch it. But the next, from 2 up to 6, this spacing means from 2 up to 6, I apply to them the spherical corrections. So what is spherical correction? How it works? Is it different than the simple equations I showed to you? If you go here and click more help module, the equation you'll find is a little bit different. So this is the gain function. So it needs velocity. It needs the velocity at each time. Velocity as a function of time. It needs the time itself. And exponential of, again, velocity t times alpha. Alpha is a parameter. T is the time. X is the location, but will not use it in here. So where I input these values. So V power, velocity power is 2. So that's the velocity power. Time power is 1. T raised to power is 1. And alpha is very, very small number. It's almost like 0. Alpha is almost 0. And X power is also 0. But most important here is this file I gave to you. The file has the extension NMO. What is NMO? NMO normal move out. They just name them like that because this is a velocity file. In later sessions, I show you how you can view the velocity files. It's a velocity file, but how I made it, how you can made a new one instead, one which is made for you, ready-made for you. So here, if you view it, that's the velocity. So this is a simple 1D velocity. It's increasing down. That's your velocity, and this is how it's interpolated. an interpolation. I does not specify each time. That's the two-way time. But I use interpolation. And how I can specify interpolation, I let you know right now. But let me close this one. If you want to create a new one, you go to list, give it a new name, a name which is not existing. So this goes to velocity, common velocity. Give it a new name and click edit. So here I go, create a file and manipulate in here. Create new column, create new like line. And what I'm saying, at time 0, what is the velocity? What is this velocity? 1479. Why I have chosen this velocity? These are random velocity. That's what you have an idea. If, for example, let's assume that you think those are sedimentary rocks, and you think this is the value supposed to be the velocity value of P wave in sedimentary rock. So these are assumptions. They might not be correct. It's fine. We later on do more velocity analysis. In seismic data processing, one of the most tedious tasks is picking the velocities, choosing the correct velocities. It's one of the hardest tasks. So this velocity 1479 is the velocity of P wave in water. So that's the direct wave which moves directly from the source to the geophone. It's moving in water, and that's the velocity of P wave in water. So the next time 200, what is the velocity? And still I'm in the water, 600, and then I keep increasing. So the first parameter is the time. This one is supposed to be 500. Sorry, that's fine. The most important is in here you can put whatever you like. But in here, in this case, since I'm reading shot 500, only shot 500, I supposed to give the primary key shot key value as 500. The rest, I'm not specifying. I'm not specifying secondary value. I'm not specifying. That's the reason you see it as 1D velocity. When I do it, it was simply 1D velocity. So this is the time. First parameter is the time. The second, the corresponding velocity, P wave velocity belonging to this time. So this is how I create it. So I don't want you to spend, many of you, I believe some of you haven't installed the software yet. So it's hard to follow along and waste our time. Let me quit. It's already saved. But here how you can view it. As you see, it's 1D. It's 1D, and that's the scale. That's the velocity scale. So it's close. First, the shallow time, the velocity of the seawater, then it goes deeper to 3,000, close to 3,000. But we'll pick later on velocity, and it's a good idea to know how to pick velocity using different techniques. But for this workshop, we'll use one technique because we don't have much time. And what are these? So I say up to time 200, use interpolation or grading value of 20. So 0, 20, 40, 60, 80, 100, up until 200. Then from 200 to 500, use a grading of how much? 25. 225, 250, 275, and so on. So from 500, I use a grading of a grading increment of 50. And after 1000, I use a grade of 100. So I need to like for the later time because if you don't specify this, it's fine. If you don't specify, but how I can learn something, for example, I'm not asking you to read everything. It's not in here. It's in NMO. It's not in here, but it's in NMO. It's saying how you can speed up the process. So this is the grid. The grid is used for interpolation. Whenever you interpolate anything, any sample values which are not regularly graded. You need to specify grade before interpolation. We have seen our velocity is smooth velocity, so it have been graded and interpolated. If you are geologists, I think you have the mapping. How you can do mapping in software? You need to grade the data, then interpolate or map it using the techniques to start. So this is spherical divergence. This is just testing. We testing how we can improve the testing and increase the velocity. Then in my loop in here, if it's not a loop, it's just if statement, and I enter another if. So this one, there are two ways to specify the repeat. So instead of for the first one, in this case, I have chosen a repeat from the first list. Then I have specified a range using values with a space in between. But you can also specify it in this way. You can choose, you can say range. So what's the difference? The difference in this case, in here you can specify exactly like 3, 5. In here you say range from 3 up to whatever in between. So in range, if you're sure that you need to run them on all of the reads, you then better use range. So the only difference between her using this technique or either this technique is in case if you want to apply this if this testing or this module in certain number of reads, data reads. So that's very simple. Then I apply scale. Scaling in this case is applied in terms of something called decibel per octave. I haven't explained this, and this is very important for geophysicists at least. It's very important. It's important for not just geophysicists, like engineers. They use it a lot. The one who deals with voices, sounds, instruments, electrical energy, they use decibel per octave. Decibel per octave is a sort of boosting the data or decreasing the value. We have two terms. Decibel, the other one is octave. Decibel is a log value, log 10 of initial value or a second value over the initial value. So log 10 times log 10 of two different values. So power, for example, or amplitude in our case, amplitude 2 over amplitude 1. How much the difference in amplitude in this case in terms of decibel. But there is another term called octave. Octave is related to frequency. Whenever there is a change in frequency, how much I need to scale the values. But I'm leaving it for today because I want to make some simple quiz on it, and you probably might understand from the quiz itself. This is not just simply related to geophysics itself, but it's related to signal processing, whatever signal processing in many domains. Electrical energy, they use this technique too. I believe geologists might use it, I'm not sure. But again, what is the grid? The grid, I use it for interpolation. And here I'm using also, I'm not using one. If I got to edit it, I'm using different ones. So for primary key, what's the primary key in here is the repeat. You can go list. So for read, for data, whenever the data is 3, the repeat is 3, I use a decibel of 6. And this one is what is the time. This is from 0 to the last time. It's not exactly 600, it's 601.48, but that's fine. So the other one is 12. Then 5, repeat 5 has a decibel per octave 16. I gave you a small quiz to calculate decibel per octave for some signals. Those signals are not geophysical signals, simple amplitude values or power values. And for the last one, I'm also using 6. I assume 6 is a good number, so I'm using 6. So I'm using different tests. So let me quit. It's already saved. And those are the grid. So from 0 to 500, I'm using grading value of 25. Then from 500 to 1000, the grading value is 50, and above 1000, the grading is 100. I end it, then I balance. Balance is equalizing my amplitudes. All amplitude supposed to be, because I'm testing them, I want the amplitude to be the same at this stage. But it might destroy your data. It might destroy your amplitude data. I don't care in this stage still if they destroy my data or not. I'm in testing stage. So the amplitude at shallow times and later times, they be equalized to viewing purposes only. Then I use panel text. So the key para is repeat again. So the first one I say no TAR, no true amplitude recovery. I don't. For the first repeat, I say that this is just a text which gonna be displayed on the shot gather. So for the first repeat, there is the text or the name of the gather supposed to be no testing. Then I'm only applying spherical divergence. Then for 3, 5, 6, I'm applying decibel. This one I'm applying decibels, not spherical divergence. So spherical divergence, you have seen the list I applied for 2 and 6. If I go back to my if, you will see that I'm applying only for 2 and 6. Let me check what the time is. Okay, so we spent almost like an hour. I will try to be faster in next jobs, coming jobs, or give you like some jobs, you just run them. Because many of the jobs, they are production jobs. In the production jobs, you don't need to test, you just input your data and output the data in a new name, as a new name after applying the filtering or after applying whatever process you selected. So that's how is it. And finally, view. So since in here I want to use header parameter, I choose panel text. I need it to be displayed as well. I need to go here, then select, you'll find it, the panel text. That's the panel text. The rest is similar. If right now I run my job, so let me just decrease the scale. This is, I created it on my PC. The PC, the scaling is different. So instead of 5, let's make it 2. Yeah, that's better. So here, this is the first one without enamo or spherical correction. This one, first and sixth, they have been spherical divergent correction applied to this one. Applied to this one, only gain have been applied, 6 dB, then 12, I believe, then 18. So you will find, if you go later times, you will find the later amplitude they are posted. They were amplified. The amplitude values were increased. But how I can prove it? It's hard to see. It's hard to see using just the shot gather 500. Another thing which is very good in this case, since we specify the trace spacing, software know right now what is the spacing between first geophone or first hydrophone to the next trace or hydrophone. If you go select ruler, so you remember I said what are we removing? We are removing the direct and the refraction. So what is the velocity you are seeing? The velocity is supposed to be here. That velocity. So without the geometry, the offset we specified, we cannot use the ruler. Ruler can only be used whenever the software knows what is the spacing between, what is the location and what is the spacing between one geophone to the next geophone, and from geophone to the source location. But anyway, how I can make a better display? Another good display is amplitude decay curves. How the amplitude decays, trace by trace. So if I click this one, select this one, and just click once without specifying an area. You can specify an area, but if you click once, it will select all the shot. So here is it. So here is it. It's how strong is the amplitude. So this one is, let's make all panels. So all panel. So this is first one. What you see in here, you see the amplitude strongest in the earlier arrivals, and there is no amplitude in the late arrivals. This is belonging to which shot? This one. If I keep moving, synchronize panels, let me see. Yes. So what does synchronize panels done? Whenever you change this one, the shot gather will be changed too. So this is quite good. This is the amplitude is quite similar from earlier arrivals to late arrivals. Maybe we're supposed to remove more in here, but that's fine because we'll be muting again. We'll do muting in later sessions. So this is fine. But here, this is not satisfying. This is not satisfying at all, as they have most the energy is on the upper part. There is no amplitude in the later part. I'm seeing the curve, it's increasing and then decreasing. But in here, I see the curve increases and stays at some level, plateau at some level. That's a good thing, that's a good signal. But here again, this is the poorest. This is totally the poorest. So right now, almost like my preference is this. I use the same spherical divergence function or module and also apply 6 decibel of a correction, decibel per octave scaling. So this is a nice view, and I'm satisfied with these parameters. So the idea in here is to test your data and see which parameter gives you better results. Let me close this one and run to the next job because we are running out of time. I don't want to keep you just viewing me without doing anything. Let's dismiss this one and save and exit. So that's TRV, true amplitude recovery, and we have seen that the velocity file we are providing is fine. It's still early values. We will improve it later on when use picking stage whenever we start picking our velocities. But for the time being, that's fine. And we approve this using the amplitude decay curves. Then I go to another flow. This flow is trying to remove a very common type of noise, which is commonly existent in marine data. So the job name is swell. Why swell? That's the name of the noise. The name of the noise is swell. I go back to mute. So number 3, job 3 is swell. So what you see in here, it's quite similar to the previous job. It's quite similar to the previous job, but there is one difference. So here I'm bringing something called repeat. You can do repeat in two different ways. One of the ways is you read the data and apply number of repeats. Another way is bring a module called repeat. So here let me just read. Oh, just yeah, just let's read 500 instead of all of them. Number of simples. One number of repeat. There are two repeats. So for butterword filter, we use two repeats. So this repeat, after this sequence, we use repeat. So, but the repeat going to be applied only for one of the modules, which is called butterword filter. If I go here, that's the module name. Butter filter, butter filter process, butterworth bandpass filter. And I tell you what is bandpass and high pass or low pass. These are type of bandpass. Here I'm applying high pass. I'm trying to remove low frequencies. So what does these things means? But before that, before going to the details, I will not explain some parameters because S-mute have been already explained. This grid was used many times. And here I'm not using all the data. I'm only applying this testing on the selected data. Another thing is this is the same. You can just use include once you start creating your job, include and bring them. There is few differences. One of the differences here, this is the same. This is exactly the same. The major difference is scale. So here I use 12. Why is that? Because I don't want to test. I'm satisfied with 6 decibel per octave. The value of 6 decibel per octave is I'm finding fine for me. Let me check everything is going fine. Yeah, let me just close this one and go back here. So this is fine. This is similar. I already gave you this file. The scaling have been done. Repeat. If I run it, I use this. You can mute it, but I was filtering sometimes introduces some noises. So I tried to apply again muting. If I run it as it is, because I changed the values, I need to change some values in here. Yeah, that's fine. Instead of 8, I'm supposed to make it 1. It's only one shot. In here it's... Oh, sorry. Number of samples is one shot gather. Number of repeats, there's 2. If I run it right now, so what is the most important difference you see between these two? Let me change the color. Make it 65 to 80. So there is some noise. You see this noise, this is swell. This is whenever there is like a wave in the marine, it creates noise. So it moves the stream. The stream contains the geophones or hydrophones. So you start moving them and creates this type of noises. If you view these noises, they are high amplitude. They are very high amplitude, but their frequency is lower than the frequencies of primaries. Those are the primaries. The frequency is lower than the frequency of primaries. Let me go again. Then, so here is this noise. It's available in here if you go to the next panel because we have applied filtering. We have applied filtering. So let me see this noise. Analyze frequency spectrum of frequency characteristic. There are many tests you can. Let me select this to see what is the frequency. Oh, not this one. Instead, frequency spectrum graph or frequency spectrum traces. This is good. So you see this, the frequency, highest frequency is below like 10. The highest frequency, the frequency, the amplitude of the highest amplitude is within the low frequencies. The highest amplitude, which is dominating these values, is within these frequencies. Let me see the panel and synchronize them. See what the difference between them. So I remove this one. What I have observed that there is a boosting in higher frequencies. So this is the frequency axis. This is the frequency axis. And this is the channel axis. So I selected only this. So that channel is 69 up to like 120. How you can select all of them, like all of it? You just go traces and click once. So it's bringing all channels. And if I go click all panels, synchronize panel, I move between them, you see I remove low frequencies. What process applied this thing? What is the module which is applying filtering, low frequency filtering or high pass filtering? Is this filter. So I say from 5 to 10, then 60 to 70. Why I haven't specified much higher, like much higher values? My frequency spectrum is my total frequency, all frequencies is not higher than 70. Another thing, I'm already applying high pass. So whatever above 10, they're going to be passed, but whatever below 10, they're going to be removed. So here is the parameter amplitudes. So these amplitudes, I does not in geophysical processing never use 0. So I use very low number, 0.05. Whatever below 5 or from 0 to 5, 0 to 10, instead it's 5. But the reason is that I cannot use 0. There is no frequency 0. There is no frequency 0. So I believe my lowest frequency is 5. You can make it 2. There is not much difference. But 10 is the cutoff. 10 is the cutoff. Above 10, I preserve all of them. And at later time, I go slope down. So the Butterworth itself, if I do Butterworth filter, so it's a filter like that. Let me see some images. It's a filter like that. So this is high pass. Yeah, it's high pass. So mostly in in electrical engineering. But you see here, so this is my cutoff. So I pass all above this frequency. In my case was 10. I pass all the frequencies above 10 and try to minimize or remove the frequency below 10. So that's how simple is it. And we have seen good improvement in removing swell noise. If I run it again, you will find that there are other noises which have been also removed. One of the noises, I made a mistake. Mm, that's fine. Let me change something in the plot. 65 to 80 and make this one a 5 to, this is fine. Let me still increase the amplitude. 0.5. You see, huge amount of noise have been removed. Another thing which is not very clear, probably here, you see that there is a feature moving in the opposite direction. Here is it as well. That's the tailboy noise. What is tailboy? If I go back to my screen, slides, um, this is tailboy. So it's on the surface, and it's moving, the ship is moving, it's hitting the sea surface and creating waves. So their energy is in the opposite direction. So their energy is the opposite direction of the ship movement. So they look like this. And if you check their velocity is very low. So how you know the velocity? So if I create some ruler, so whenever you make this one steeper, you'll find the velocity lower. Whenever you make it gentler, the velocity is higher. But their velocity in the opposite direction. Their velocity is in the opposite direction. Okay, I need to run again. So the velocity is negative. It's not negative velocity, but that's how, because the velocity is calculated in a way that we take these traces to these traces. Shallow traces, narrow traces to the farther traces. But these, they have low velocity. So their velocity is even lower the velocity of P wave in water. These are positive velocities. So that's it for today. We will cover later on more jobs. Some of the jobs I just send them to you and you need to do them yourself. Thank you for listening. Right now, stopping the stream.